A lot of noise, a lot of cars and traffic, and I guess we're just going to see what happens, right? Because it's the best we can do right now. All right, so welcome back, everybody. There are 4 different large bodies of ocean, and sometimes we'll throw in a 5th one, and people break these up in different ways, but they're really all connected to one another. So our 5 big oceans that we're going to learn in this class are Pacific Ocean, which is right off our coast here in California, the Atlantic Ocean, the Indian Ocean, Arctic Ocean in the north, and the Southern Ocean in the south. The Southern Ocean sometimes is not named, but we'll call it the Southern Ocean in this case. And in this table you can see the average size of them, and you can see that the largest and the deepest of them is the Pacific, then followed by the Atlantic and the Indian after. All right, and then there's a number of what we call seas: Mediterranean Sea, Coral Sea, Bering Sea, Red Sea, so forth. And you've heard of these before, probably, and sometimes they're called a Gulf. For example, Gulf of California, Gulf of Mexico. And these seas that I have here on the list are the ones I want you to know. And what I'll do is I'll show you a map like this, and I'll ask you where they're at. The difference really between a sea and an ocean really, first of all, is there really is no difference because they're connected to one another. But in geography, primarily, when geographers are plotting out coastline and things of that sort, a sea is usually referred to a place that's sort of closer to land. So wherever an ocean is closer to land or is surrounded more by land, they call that a sea. And some of them are entirely surrounded by land. For example, the Caspian Sea is the largest lake in the world, but it's actually a saltwater body lake, and therefore it's a marine environment, the Caspian Sea. So some of them are entirely surrounded by land, but that's how we'll use it here. And as long as you know those, that'll make sense as we go throughout the class when we talk about different locations where animals are. Okay, now this is just a view of the Arctic Ocean, again in the north if you're looking down onto the North Pole, and then the Southern Ocean if you are looking up onto the South Pole, looking upward from the South Pole up, if you can think of it that way. Up and down is all relative to where you're at, but I'm sort of gauging it on a map of the world as you've probably seen it, and using us in North America as kind of our point of reference. All right, so we have what we call crust. If you think of the dirt, you know, the dirt of land, and there's what we call oceanic crust, and there's continental crust. And they are slightly different based on their chemical structure. For example, oceanic crust, we also call basalt. It's usually denser at about 3 grams per centimeter cubed, and it's only about 3 miles thick, which sounds like it's a lot, but when you compare it to continental crust, which is 12 to 30 miles thick, you see it's actually kind of not very, it's quite thin. It's geologically young, whereas continental crust is geologically much older. And when we're talking about geologically young and older, we're still talking millions of years, tens of millions of years. Oceanic crust is darker in color, continental crust is lighter in color, and oceanic crust tends to be more rich in iron and magnesium. Continental crust tends to be more rich in sodium, potassium, calcium, and aluminum. The density part is really going to be important if you think about that coming up here. Okay, so the next thing is, if we took the earth and you started to dig a hole into the dirt, you would be digging in the uppermost layer of the crust, and the uppermost layer of the, assuming you're on land, of the continental crust, if you keep digging and you go many, many miles deep, which, you know, you would have trouble doing that, you would get a little bit deeper. You get to the outer layer, the uppermost layer of the mantle. So the crust and the upper mantle together are what we call the lithosphere. And the lithosphere is solid, it's rigid. If you were to go deeper than that, so now you're many, many miles deep, you know, you're 70 miles deep into the earth, you would hit deeper into that upper mantle, which we call the asthenosphere. The asthenosphere is the upper mantle that is more flexible. It's like plastic. And that's because as you go deeper, it is getting hotter and hotter and hotter because there's more and more pressure. So the pressure is driving up the temperature as you go deeper. I'm not talking about just, you dug a hole and you're 3 or 4 feet deep. I'm talking about your hundreds of miles deep. It would become plastic and more flexible because of the pressure it's under. So as you go deeper, it becomes hotter to the point at which it's almost at the point of melting rocks. And if you go deeper than that, into the lower mantle, into the core, it is in fact a liquid of melted rock because it is so hot at those temperatures that it melts rock. Okay? Now, what happens is at different places throughout the earth, there are weaker spots, there are weakening spots where the deeper layers of the mantle push upward and crack through the lithosphere. And those form in the ocean what we call a ridge. And what happens at a ridge is you have really, really extremely hot, high pressured, melted rock pushing up to the surface, and because it's coming to the surface and it's reduced in pressure and there's all this extra water cooling it, it tends to solidify and it becomes rock, being pushed by the fact that you have more of that hot melted mantle pushing upward. Plus, at certain points, as one plate, as we'll see, as one of these plates of rock hits another, one of them will dive under the other one and it will pull the rest of it with it. So wherever you have this hot mantle coming up and forming a break in the crust, we call that a ridge. And so we've already seen several of these ridges running along our maps, and that's what those are. Those are areas where the mantle is pushing new rock up, and we call that seafloor spreading. And that's why oceanic rock tends to be very young, because that's where you're making brand new rock. That is melted rock that didn't exist before, and because it's coming up to the surface and cooling, it's becoming new rock that wasn't there before. New oceanic crust. That doesn't really happen on continental crust. It really only happens in oceanic crust. So that ocean floor tends to be new. Now, if it's constantly growing, as we'll see, if the Earth isn't getting bigger, then you got to have something disappearing somewhere. If you're adding new stuff, something's got to disappear, which it will, and we'll see that just in a minute here, okay? So that's what's happening at these ridges, and you can see in this little animation here, you can see seafloor spreading. All right, now what that means then is throughout Earth, if you took our planet, you have the continents, which you already know about. Well, those continents then are actually sitting on also on these lithospheric plates, and sometimes the lithosphere surrounds a continent, sometimes it is part of one continent and it touches another one. So there are several different plates that we call lithospheric plates, and those plates move when the seafloor is spreading, and that whole idea of seafloor spreading and moving those plates is called plate tectonics, which you've probably heard of before too. So the Earth, with all these continents on it, is not staying exactly where it is right now. It's moving somewhere between like half an inch to 10 inches, I think, per year, or somewhere along those lines. They basically are moving at about the rate of your fingernail growth. Sometimes a little less than that, sometimes a little bit more, but your fingernails growing at a certain rate probably a good idea about how fast they're moving. This shows you where all the plates are at, and you don't need to worry about where all the plates are at because I'm going to mention a couple. You just need to know the examples of them, okay? So 190 million years ago, all the continents, it turns out, were connected into one big supercontinent we call Pangaea, and at that time there was also one big giant ocean called the Panthalassa Ocean. The Panthalassa Ocean covered the entire Earth, and there was just one big giant super ocean at that time. And around 135 to 150 million years ago, Pangaea split into two super big continents, not as big as Pangaea obviously, but they became Laurasia, which is in the North America, and Europe became Laurasia, and Africa and India and Antarctica and Australia all became what we call Gondwana, which means southern land. And those continue to split apart, and now the continents are where they're at now. And they're still moving, of course. And there are models that show what will happen in whatever 200 million years or so. All the continents are going to move back together again. And then they're going to separate again. So they're constantly doing this. They're moving and floating on these lithospheric plates as the plates grow and push the continents around. And there's all kinds of evidence that supports it. For example, if you take Africa and you take South America, you can see just by the shape of them, and it looks like they would fit together. It looks like they were maybe somehow puzzle pieces at one time. And in fact, what we find is that if you compare fossils found in those regions of Africa and in South America, they match based on the geological history of those areas. So not only do the continent shapes match, but the fossils we find there match what we find in evolutionary history. Okay, now what happens when these plates hit one another? Well, they do different things. If you have an oceanic plate and it hits a continental plate, then it's real simple. What happens is the oceanic crust plate is denser, and so it will always go under the continental crust, resulting in what we call a subduction zone. And along the coast of South America, the Andes Mountains, we have an example where the Nazca plate is hitting the South American plate, and it forms what we call the Peru-Chile Trench. And whenever you have a continental plate that is being hit by an oceanic plate, the oceanic plate is going under that plate, and that results on the other side. On the other side of the trench, you get volcanoes and you get earthquakes. And so that's what happens in regions like that. And an example again is the Andes Mountains and South America. You get earthquakes and you get volcanoes. Okay? Now, what if you have a continental crust plate that hits another continental crust plate? Well, that happens where India hits the rest of Eurasia and continental crust hits continental crust. Neither one of them are dense enough to go under the other, so they just build up, they buckle. And what you get is that's where you get mountain ranges forming. Eventually, some of that crust does get buried on whichever crust is denser based on chemical composition, but because they're both about the same density, they run into each other and they just buckle and build up. And that's one of the ways we get mountain ranges. Okay, what if you have oceanic crust and it's hitting another oceanic crust plate? Well, you get another subduction zone then, and one of the plates, whichever one is denser, manages to get under the other one, and you get, and again, this is oceanic plates, so there's in the ocean. So you're going to get, once again, you're going to get volcanoes building there. And because they're volcanoes and because they're in the ocean, they many times will cool and surface and form islands. So the Aleutian Islands is an example of those. So you get earthquakes there, and you also get volcanoes there because you once again have a subduction zone because one plate is going underneath another plate. Okay, now what if they go side by side? Well, an example of that would be what we have here in the San Andreas Fault, and we call this a strike slip fault. So the plates aren't hitting directly. Instead, the way that they're moving, one is moving to the side of the other, slipping past each other. And what happens is they build up a huge amount of tension in these two big, huge pieces of earth that are being pushed the opposite way from one another. Again, a couple of inches per year. But because they're pushing against each other, every now and then the force that's holding it in place is too great and it slips. And whenever it slips, that creates the scenario for an earthquake. And once again, the San Andreas Fault is a good example of that. Similar to what we're just talking about here, this instead of being a trench, this is what we call a stationary hotspot. So occasionally you'll have weaker areas in the lithosphere where the mantle is leaking out and it's forming volcanoes, and it's a hot spot. So as the plate goes over it, and because the earth is curved and because the plate is moving over it, what you end up with is this chain of volcanoes forming. An example of that ends up being the hot spot islands, which are in fact the Hawaiian Islands. And so if you look at those, you can see that they're curved. And you can see also that Kauai is the oldest of those, somewhere around 3.8 and 5.6 million years ago. And then Maui, for example, is only less than 1 million years old. All right, so that's it. That's a basic little introduction to marine geology and geography. And I will talk to you all soon. Have a good day.